Hey there, this is Math 148, looking at section 11.2. So section 11.1 was all about logarithmic functions, so guess what section 11.2 is? That's right, exponents. So where there's logs, there's exponents. So we have 4 different rules in this section, and the first is considering a function like this. The first of these functions we consider are all e to the x functions because they are the simplest. So suppose we have a function that looks like y equals e to the x. Well, here is rule number 1. There's basically 4 little rules in this section. Obviously, you don't have to have the rule numbers memorized. If you have a function that looks like y equals e to the x, the derivative of this function is e to the x. What? It's the same thing. That's pretty awesome, right? Why is this true? How can it possibly be the same thing? There's a short little derivative explanation, that is how they find the derivative, on page 710, but I'm not going to require you to derive this derivative formula. Just remember that if the formula is y is e to the x, if that is your function, then the derivative of the function is also e to the x. Here's an example of this. Suppose we have question number 1. We have our function y equals 5 times e to the x minus x. So our derivative, we're going to use our new rule. This is a constant. The 5 is a constant, so we can factor that out front. The derivative of e to the x? Yes, e to the x minus the derivative of x is 1. So I'm just rewriting this, although I don't really need to. 5 times e to the x minus 1. Do you guys like this section, right? That's a nice rule. So you guys are definitely going to want to have this memorized or have it written down someplace. Here is another rule. Rule number 2. We have and again, these aren't numbered, they're just there's 4 basic things we're covering in this section. This is a chain rule application of the same thing. Suppose you have a function that looks like e to some other function. So it's e raised to something complicated. Then the derivative of y is equal to e raised to the complicated function. So you leave this unchanged, and then you take the derivative of the complicated function. So your book writes these as dy dx equals e to the u times du dx, but it's the same thing, like this. Oops, that's a d, fancy d. So essentially, you're going to take the thing, you're going to write the function and leave it the same, and then take the derivative of the exponent. So here is an example of this type of problem. Question number 9. Suppose we have y is equal to 6 times e to the 3 times x squared. So all of this is the exponent. So now our exponent here is sort of complicated, but we're going to use our new chain rule function. So the constant stays out front, it just stays there. So first of all, you write the whole e to the exponent part. You just leave it unchanged, just copy it down. Make a little genetic copy right here. Now we take the derivative of this piece, which is 6x, because the derivative of that right there, 6x. So our answer is 36 times e to the 3x squared, like that. You have to be a little bit careful when you're writing so that I can tell where the exponents are. So don't just write this, 36e3x squared. Don't do that. Okay. Here's another one. This question I'm going over mainly because it's just a little tricky. I don't know. It's clever. Is it too clever? I don't know. It's y equals natural log of x cubed. Okay, so the thing that they're doing with this problem is reminding you, and me, because I've had to remember it, that e to the natural log of x is equal to x. So we can actually rewrite this same equation as y equals, this whole thing is the same as y equals x squared. They are the same function. So now that we know that this function is y equals x cubed, I said x squared before, it's x cubed, we can say the derivative is 3x squared. So the derivative of this complicated function, y equals e to the natural log x cubed, is just 3x squared, and that's because this function can also be rewritten as y equals x cubed. So question number 13 is really just making you practice these rules of kind of exponents and natural logs. So this is rule number 2. I said there's 4 rules. I was not lying. I would never lie to you guys in videos about exponents. So here's another rule. Suppose we have a function that looks like this, y equals 4 to the x. So we don't have a e function. It's raised to some other power. It's not note, but not e. So here's our new function. Here's our new rule, that is. If you have a function that is y equals a to the x, where a is some number, then the derivative of that function is equal to a to the x, you leave it alone, make your carbon copy, times the natural log of a. And again, I'm not going to ask you to derive this, I'm just going to ask you to use it. So here is your rule. And here is an example of how this would look. Question number 32. Suppose you have this function, y equals 3 to the x. Okay, so the derivative of this function, I'll make it yellow, the derivative is equal to, we're using this rule, first of all you just write it the same, make your little carbon copy, you haven't changed it, just rewrite it, 3 to the x. Now we take natural log of the new base, which is 3. And that's your answer. And remember that this natural log of 3, that is a number. You can type it into your calculator if you don't believe me. The number is 1.0986, something like that. So this natural log of 3 is a number. It's a constant number. So that's how you do that problem. And this was the third rule to consider. So we have one more variation on this rule that I wanted to point out for this chapter. So the last thing to keep in mind is, suppose you have a function or an equation that looks like this, y equals 4 raised to the x squared plus 5. I had to raise my voice because I'm speaking in exponents. So now our function is more complicated. So you have some constant, right? There's a constant that's raised to a complicated thing. Here is the new rule. This is the final rule. Suppose you have y is equal to a, some number, raised to a function, some complicated function. Then the derivative of y, your book writes this dy dx, same thing, is you just do your carbon copy again, you leave it alone, a raised to the complicated function, times, you take the derivative of the complicated function, du dx, that's the derivative. You could also think of that as u prime. And now we take natural log of a. Again, I'm not going to ask you to derive these and say where they're coming from, because you're not math majors, darn it. But this is our function. Excuse me, this is our new rule. And I'm going to show you an example of this one. This is question number, that's a Q, 34. Question number 34, you have y, your function, equals 5 raised to the 2x minus 1. That's all in the exponent. So we have, when you see this function, there's a couple things to keep in mind. One is this is the base and it's not e, okay? And the other thing to keep in mind is this is some complicated function. So to take the derivative, we're going to use this formula. So first we rewrite the whole thing exactly as it is. So it's 5 to the 2x minus 1, like that. And now we take the derivative of the exponent piece. So the derivative of this one is 2. That was easy. And now we round it all off by taking the natural log of the base. So that's natural log of 5. So the whole answer is 2 times natural log of 5, remember that's a number also, times 5 raised to the 2x minus 1, like that. And that's maybe not your favorite looking function in the world, but that is in fact the answer. So that gets you basically all the way through section 11.2. There are also a few application problems and you can look at those. I wrote out the homework solutions, so check those out and let me know if you have any questions.